fact, the abstract you have in this booklet is about this, because it was communication, let's say, for all, because I sent an abstract for the course, and this was supposed to be for the conference. And now we are mixing both. Then I gave the lecture for the school. Now this is supposed to be a talk in the conference. It's about some research and in these recent years. In fact, it continues. It's again about deformations, but now it's a different sort of different kind of deformation, what is called a Q deformation, and this Q deformation or quantum deformation led to so-called Hom-type algebra, which twists the defining condition of the algebra. Let me start with what they call a paradigmatic example, and everybody knows SL2, and then it's given by these brackets. It's three-dimensional algebra, and if you can write it in terms of differential operators, and in terms of differential operators, this element E corresponds to the partial derivative, and h to minus 2t. Then of course here we are dealing with polynomials with variable t, and h is minus 2t d, and f is minus t squared d, and this is a basis. And now if then it defines an associative algebra, and the Lie algebra is given by commutators. Then if you take the commutators of these three operators, you get your SL2. Okay? Then now, Q deforming this SL2 means that we replace this usual derivative by so-called sigma derivation. And what is a sigma derivation? We fix the commutative associative K algebra, and the map sigma from A to A, which is an algebra endomorphism. And with respect to the sigma, we define a sigma derivation on A as a K-linear map, d sigma, satisfying this twisted Leibniz rule. I mean, usually d of AB is dAB plus ADB, right? That this is the usual Leibniz property. If you have a d of AB, then this is dAB, like this, plus ADB. Okay? And now what we do here is we modify this by considering sigma of A. And if the sigma satisfies this, then we say that we have a sigma derivation on this polynomial algebra. Now the question is, we are interested in understanding how looks the commutator in this case, and what kind of algebra we get. Do we get still Lie algebra or not? And one example of these Q derivations is given by Jackson, and this example exists since 1906. It's a very old example. It's defined on polynomials by the following. You take a polynomial pt, and d sigma of this pt is given by p qt minus pt over qt minus t. And here, this is a sigma derivation in which sigma of pt is, you consider, you take your polynomial and you replace everywhere t by qt, and then you get this sigma pt. And it turns out that this sigma is a sigma derivation. You can check that it satisfies this condition. Now let's see what happened with the sigma of d sigma of t squared, etc. How behave the monomials of your polynomial. Then sigma of 1 is clearly 1. Sigma of t, we define it as qt. Okay. Now, then d sigma of 1, according to this definition, this is 0. D sigma of t is 1, and d sigma of t squared. And to get this d sigma of t squared, you have to use Leibniz rule. And using Leibniz rule, you get that d sigma of t squared. This is sigma of t plus t, d sigma t, which means here that this is qt plus t. And at the end, we have a general formula for this, and d sigma of t to n, and this is equals to the q number n, and it involves q numbers, the q number n, which means 1 minus q to n over 1 minus q. Oops. Something happened. Huh? Connection. Okay. Okay. Then this is the general formula. Then we need the q numbers here. That's why it's called Q deformation. And now we use this deformed commutator. And the commutator here is different from the usual one. It involves also sigma. And if you consider this bracket, and what you get is the bracket of HF is equals to minus 2QF, and the bracket of HE is the 2E, and the bracket of EF now is 1 over 1 plus Q. And the question now is whether this new bracket still gives us a Lie algebra. And this type of example was considered by physicists in the 90s. Yes.
How do we arrive at this bracket? This new bracket?
This one?
No,
this?
Yes.
But this is a bracket we consider in the case you have a sigma derivation.
Okay.
Because if you consider the usual bracket, you don't get anything. Okay. And this now, if we check the Jacobi condition, it turns out that it is not satisfied. But what is satisfied is something similar, but with a modification in this level. Usually for Jacobi condition, you should have here A d sigma, B d sigma, C d sigma, and take cyclic summation. But here we have sigma of A. Then this Jacobi condition is modified by this homomorphism, and these examples were considered in works by physicists. All these people are physicists, Japanese, and in fact they were interested in twisted discretization of vector fields, and in this algebra of vector fields they consider this Jackson derivation, and they got this new bracket, these Q deformations of Witt and Virasoro algebra, and it turns out that what they got was not really algebra, but they just wrote things like this, and you can find this kind of example also in works by people from St. Petersburg, Kulish, Lukersky, Sheshian, and also this guy, I think he is Greek, from Greece, but he was connected to this school, Chinese, and also some physicists from the United States, from Miami School. And all these people arrived to some examples in which the Jacobi condition is no longer satisfied. For example, let me show you this second example. Now, consider the Witt algebra. You can view it as the algebra of derivations of the polynomial Laurent polynomial algebra. And if you take the sigma derivation I mentioned before, what you get is again a new bracket involving Q numbers here. And again, this if you try to satisfy this does not satisfy Jacobi condition, but it satisfies some condition similar in which you have coefficients here which are different, which means that we cannot factorize by this. And this was the motivation for Hartwig Laschen and Silvestrov in 2005 to introduce a new type of algebra, and they call this algebra homely. This home for homomorphism, because this algebra involves homomorphism, and it's defined by triples with vector space, a bracket, and now a new stuff, which is this homomorphism alpha, and we need the bracket to be still skew symmetric, but this Jacobi condition is modified by this so-called Hom-Jacobi condition. You can see that here we have this alpha x being here. Okay. Then in the original definition in this paper, they also assumed that this bracket, this alpha, is an algebra map, which means that it satisfies this condition. But we remove it later, and we call this the homely algebra, which satisfies, moreover, this condition, multiplicative homely algebra.
So alpha is the automorphism?
No, just a homomorphism. No, not invertible.
So, like in the other case, we had in sigma was an automorphism.
Yes.
But in this case, it's alpha is just a
marginal. Yes.
And the derivation, there is. So alpha should satisfy this additional condition.
Yeah. But it's even not, in this definition, it's not even an algebra morphism. It's just a morphism. Huh? Okay. Then the question arises, I asked it to Sylvester when we met for the first time in Spa in Belgium. I asked him what kind of associative algebra we have, which is compatible with this homely algebra. The answer was no. I don't know. And we tried, and then I suggested this modified Hom-associative algebra condition. Then now we define the corresponding associative algebra for this homely algebra will be given by again triple with a multiplication mu and a map alpha, in which this associator is modified by this alpha. Then we have the Hom-associativity condition is defined like this. Instead of having the usual associativity A, B, C equals to A, B, C, now we will divide this by this alpha. We have alpha here and alpha here. And then this is what we call the Hom-associative algebra. And here we define morphisms. Then morphism should satisfy the usual condition, and also they should be compatible with the twist map. Yes.
So when you say associative algebra, are you looking for a universal enveloping of the original homely algebra? I mean, does that do this?
Then later we can consider the enveloping algebra. But now Hom-associative algebra is just the generalized notion of associative algebra. But for the moment it's not related to the homely algebras. But we will relate it later. Huh?
So does it turn out to be this?
Yes. we can. Then we can now the first test. The first test should be to check that if you consider the Hom-associative algebra and you take a commutator, you get the homely algebra as usual. We have this to generalize this functor D, and again we need to generalize also the functor giving the enveloping universal enveloping algebra. Okay.
So the examples you were mentioning about the deformation of the bit algebra and all those examples, they are special cases of the homely algebra.
Okay, of course, yes.
Homely.
Yes. Now now this defines the morphism. And now what about the unitality? Then it turns out that the unitality is a bit tricky here as well. It's not defined as usual. Then we say that the element 1 is unit if mu of x 1 is alpha of x, not x. And it's a big difference, but it works very well. And of course, you should assume also that alpha 1 is 1. Now this is the notion of unitality for this Hom-associative algebra. Then there were lots of research was done around this type of algebra. Let me mention some results. Then, as I told you, the first test was to check that if you take a commutator, the same vector space and the commutator, then you get a Homologically algebra. And this is true for
usual commutator?
Yes, this is usual commutator. Then if we have a Homologically algebra, Hom-associative algebra, and then this with this bracket and the same alpha with x y is x y minus y x, and this is Homologically. Okay. Then this functor and for morphism it works the same. And again, of course, then we should consider the question: what is the free Hom-associative algebra? Then the free Hom-associative algebra is also interesting to construct here, and usually we can represent free associative algebra by trees. And here also what Donald Yao did for this type of algebra is to consider free Hom-associative algebra using trees. But now we have to decorate the trees, and usually you have a tree like this, showing, for example, this is A of A, B, C, and this is A, B, C, like this. And now you have to add decorations. And these decorations, for example, numbers here, if I add here 2 and here 1, and this means that I have to consider, and of course I can also decorate by 1 here, 0, 0, and this is, and for this one is with the decorated tree, this is alpha of A, B, alpha 2 of A, B, C. And if you take decorated trees, then you get a free Hom-associative algebra, of course up to some relation.
Is something missing? You have a 1 in the lowest node.
But this one is sorry, you are right. Yes, again with alpha here. Yes, thank you. Okay. Then of course in this case we try to extend Harshad homology to this case, and we constructed for multiplicative Hom-associative algebra a complex which fits with deformation theory as well. And for representation theory, there is a nice work by Yunhe Cheng, and parallelly we did something with Benayati. And for models also were defined first by Sylvester and me, and then developed by Donald Yao. And recently we discussed also these groups and some geometric aspect with Camilo Onrangu and Teles from Coimbra. And there is lots of work done now around this algebraic structures. And of course, if you have, then we can also extend. This type of algebra and then get dual algebra, and the dual and we get the coalgebra. Then the coalgebra is given by this condition. Then the condition of co-associativity now is modified by this beta. Then this is the Hom co-associativity condition. And the unitality also is modified, and again, instead of having here the identity, we have beta, the twist map. Okay. To get Hom by algebra, we can consider, in general, we have in the first papers, we consider the general situation where we have two maps, alpha and beta, when one for the Hom-associative algebra, alpha here, and the other for Hom-associative algebra, and we assume that the linear maps delta and epsilon are Hom-algebra morphism. And from this situation, we can construct again a convolution product as usual, and it turns out that if you have a Hom by algebra with respect to this definition, then this convolution product defines a Hom-associative algebra morphism on the set of the morphism of A, and where the twist map is given by this, it involves both alpha and beta. Okay. Then what will be a Hom-algebra here is the same. We define the antipode, and the antipode is the inverse of the identity for with respect to the convolution product I mentioned before, right? And of course, here also we can extend this definition and define what multiplicative means. We have multiplicative Hom-algebra or Hom by algebra if alpha is an algebra map and beta is a co-algebra map. Okay, and since this general definition, two directions were developed. The first one, we consider beta and alpha the same, and the second one, which was initiated by Canopy and Goivert, where they considered that the beta, the map beta here, being the inverse of alpha. This means that we should assume that alpha is invertible, which is a sort of restriction, but it works, and it comes from some categorical discussion, which over here. Okay. Then these are called monoidal Hom by algebra or Hom-algebra. Okay. Now there is Donald Diao showed a very nice trick to construct this kind of algebra. In fact, if you start with usual associative algebra, but it works also for Lie and for many right structures. Start with A that's going to U, associative algebra, and then construct new multiplication, and of course, sorry, and what we need is an algebra morphism, an alpha from A to A, algebra morphism, with respect to this associative algebra, and then this leads to the Hom-associative algebra defined by the composition of alpha composed with mu and alpha, and this is a Hom-associative algebra. Okay. Then of course, then what you need is just usual associative algebra. For example, just associative algebra and an algebra morphism with this multiplication, and then you compose your multiplication by alpha, and you consider this alpha to be the twist map, and you get a Hom-associative algebra. And the same holds for Lie. And this we can say that, and of course here is you can also generalize this construction. Now, if you are using if you start with a Hom-associative algebra, then the generalization of this is the following. If now we start with a Hom-associative algebra, that's denoted by A mu beta, And if alpha is what we call a weak algebra morphism. Weak algebra morphism means that we don't need the second condition in the morphism. We just to have alpha composed by nu. This is nu composed by alpha tensor alpha. Huh? We need only this condition, not the fact that this alpha and beta should be compatible. And you can construct from this new Hom-associative algebra by considering beta composed with nu, and here beta composed with alpha, and this is a new Hom-associative algebra. Okay, and we say that we have here that if you consider the category of Hom-associative algebra, then it's closed under weak morphism. And of course, you can construct a bunch of Hom-associative algebra starting if your algebra is multiplicative, which means that it satisfies this condition. And we extended this to Hom-algebra. If you start with the bi-algebra, here you consider only the particular case. Start with the bi-algebra and beta to be a bi-algebra endomorphism. Then you can modify the multiplication by composing by beta, and the co-multiplication by composing by beta from the right. And then what you get here, and then consider this to be the twist map. And what you get here is a Hom-algebra structure. Okay. And now this allows me to show you that in this case we can also deform this quantum groups. Then I start with the quantum group SL2. It's defined by these relations. This is the multiplication, but the co-multiplication will be defined later. And then here we can have a family of bi-algebra morphism with respect to this quantum group. And the bi-algebra morphism are defined with the parameter lambda. Then alpha e of lambda alpha of e is lambda e, and alpha of this lambda should be different from 0. Then alpha of f is the inverse 1 over lambda of f, and we keep alpha of k equals to alpha of k. And with respect to according to the theorem I mentioned before, this proposition, then the deforming multiplication and the deforming co-multiplication with this alpha becomes a Hom-algebra. Okay. Now we in work with Florent Barnighty, we extended this Yao twist, and also considered some twisted tensor products and smash product for this Hom-associative algebra. And then we define what we call alpha pseudo twister. This pseudo twister exists already, and they were defined by Florent Barnighty and Fred Van Ostein. And now we start with an associative algebra. I claim that this theorem is a generalization of this Yao twist. Now we start with an associative algebra, an algebra under morphism, and also a map going from A tensor A into A tensor A, and with two maps going from A tensor A tensor A into A tensor A tensor A, and satisfying these four relations, these four conditions. And the first one means that it should be compatible with this T, and we have some condition. And if you have this the T satisfying this four condition, then this is called the alpha pseudo twister, and the maps T1 tilde, T2 tilde are called the companions of T. And it turns out that with this T, if with this T satisfying this four condition, if you compose by T from the right, and you consider this alpha here, you get a Hom-associative algebra starting with this data. Okay, and And this is the part the Yao twist is a particular case of this by considering this alpha morphism and T is just alpha tensor alpha, and these companion maps are defined in this way. Okay. Then if you have this situation, these T's, then the alpha T I mentioned before and the alpha and the A alpha given by this Yao twist are exactly the same. Okay? We can now generalize these constructions and get more Hom-associative algebra starting from a Hom-associative algebra. Then we start with a Hom-associative algebra defined D, and then the linear map T, and the two maps T1 tilde, T2 tilde, and we define now what we call the Hom twister, pseudo twister, sorry. Before it was alpha Hom pseudo twister, now this is just Hom pseudo twister, which is a generalization of pseudo twisters. It should satisfy these four conditions, which are slightly different from the previous ones. And again, here we have this dt. The main difference here is we are just using the alpha coming from the Hom-associative algebra. And before it was alpha coming from an algebra map, and what was fixed first was an associative algebra. But here we fix a Hom-associative algebra and we use its alpha in the condition, and this dt defined in this way, it's again a Hom-associative algebra. Okay. Now we take a particular case, which is called Hom twister. Now we don't need this companions map, but just T, just a map T from D tensor D to tensor D, and we fix this Hom-associative algebra. If our T satisfies this four condition, this T1 3 means that you put the first let's say component of T in the beginning and the identity in the middle, and it's like for IISER equations and so on. I guess I don't know if you are familiar with these notations. This T the T of let's say X tensor Y. You can write it as a sum of, let's say, using this Sweden notation, AT times A1, A2, and if you then T1 3 is a sum. That here A1, you put A1 here, tensor the identity in the middle, tensor A2. This is the notation we use here. Okay, and such a map is called the Hom twister, and in this case we have again a Hom-associative algebra corresponding to this T, where the multiplication is twisted by this T. Let me show you some example, which we computed by a computer algebra system, defined with Mathematica, and then it's easy to construct examples with this. Then we have here a family of Hom-associative algebra in dimension 2, and we can construct Hom twisters like this. We have families of Hom twisters. To this family of Hom twister, because it corresponds to a new Hom-associative algebra. If you remember, then this is commutative, and here it's no longer commutative. Then you have we produced a new Hom-associative algebra. Okay, then now we consider an associative algebra, an algebra endomorphism, and a pseudo twister. And what we want to show here is if we start with the situation in associative in classical case, then if we apply this Yao twist and again this modification of deformation by this pseudo twister, then it's the same as applying this T operation and then the Yao twist. This is what playing this theorem. It's the same.
So two operations commute with each other.
Yes. You can first apply the Yao. If you start with associative algebra, you apply the Yao twist and then T. It's the same as applying to the twister, the pseudo twister, and again the Yao twist. It's the same. And now I will show you that we can also twist the tensor product. I mean, you are certainly used to when you take the product or the tensor product of two associative algebra. What you do is just multiply by taking the flip, right? If you have x1 tensor x2 multiplied by y1 tensor y2, and this usually is you flip these two and apply the multiplication. X1 y1 tensor x2 y2, right? And you use the flip here too. But in fact, you can. There is also other possibilities to get multiplication in the tensor product.
How do you use the flip in this one?
Here you flip these two elements. This y1 becomes here.
So the product becomes x1 y1 tensor.
What you have is, for example, this A tensor B, and the multiplication here. Then what you do is cross or tensor A tensor B. This is your multiplication. What you do is you have a flip here, which is a map. This tau gives you this B tensor B, and then you apply the multiplication here in A and the multiplication here in B. Okay, and now we can look for what kind of maps are flips this B tensor A into A tensor B. Gives you still an associative algebra. This is what is I want to show here, but extended to Hom. Then this is called twisting. Then we twist. Then we go from B tensor A to A tensor B by a twisting map. And we have a twisting map if the R I mentioned here for the Hom-associativity case, and also this is true for in general. You have to take just alpha equals to identity and get the situation, classical situation. And if it satisfies this, then we call this a Hom twisting map. And the particular case is exactly what I mentioned in the beginning, is R of B tensor A is the usual flip. And now if you do this, then you get a new multiplication. Then the multiplication of the tensor product A tensor B, where A and B are two Hom-associative algebra, and R is the Hom twisting map, and then you have this. The multiplication is defined in this way. You take your twist, and what you get is a new Hom-associative algebra on the tensor product. Okay. And usually this twisted tensor product is denoted by A tensor RA, where R is your Hom twisting map. Okay? Now we try also to compare this Yao twisting with this twisted tensor product. Then if you consider now you start with two associative algebra and twisting map, classical situation. If this twisting map satisfies moreover this condition, then we will have a Hom twisting map for this A alpha A, B alpha B, and taking the twisting the tensor product of the Yao twist of A and B. It's the same as taking the twisted tensor product of the A and B, and then take the Yao twist. Okay. I don't know how much time I still have. Maybe 5 minutes. Okay. Okay. Then the notion of models in this situation is also different, slightly different. It involves this twist maps. Huh? Then all these concepts, usual concepts are generalized to concepts involving this twist map. And we say that we start with the Hom-associative algebra. Then we have a left A model if we have a map. Huh? If we have a map going from A tensor M to M satisfying this condition, and we need also a twist. It's a vector space, and all the data here, are given by pairs. Here is vector space M and the map on the insert map alpha M, and these two conditions will be satisfied. Okay.
Now what is the condition 20? What if you have a
This is the usual condition for model.
What if you have a 1 somewhere?
1.
A or A prime.
Mm-hmm.
Say prime were 1, then what are you saying?
Then this is exactly what we have here. If it's 1,
No,
then here we should, if A prime is 1, then it becomes A1 M should be alpha M1.
But there is no alpha.
Yes, because maybe it's not written here, but with the units, it's like this. That 1 M, 1 AM, this is alpha M M. This is the condition. Huh? And then if you have 1 here, it's exactly this. And from this alpha and A of A1, this is alpha A, and this is and this is A. Huh? Then I told you that alpha A of any A, this is alpha A. And for models, the 1 acting on M is alpha M. Okay, then we define the morphism. Okay, again here if you have Hom-algebra, we can define this H action as usual. For to define left H module Hom-algebra, we need one extra condition, and the usual condition is modified to this one, involving alpha of H squared. This is the compatibility. And now we have also some. We can twist models here. We start with the bi-algebra and the left H module algebra in the usual sense. And if we have if alpha H is a bi-algebra endomorphism, alpha A is an algebra morphism, such that we have this condition satisfied. Then this modified this alpha of H alpha defined in this way is a Hom-associative this is a Hom-associative bi-algebra, and this A is a Hom-associative algebra, and the action is as zero. Okay, we can also deform this the Hom's match product. Now we use this the R, the R, the twisting map defined in this way. If you have this Hom twisting map R, and using this twisting R, we can define the structure of Hom-associative algebra on A tensor H, which usually is called the smash product. And now in our situation is defined in this way. And now we can for example define, we can twist the usual action of U du QSL2 model on, for example, on the quantum plane. And here we have to modify the structure here, the structure of the Bi-algebra, and we have also to modify the action. And now, if we consider the quantum group QSL2, then we can define using this. Here you can see the co-multiplication, and using this algebra map, we can modify it and get the Hom-algebra. And now you can consider the quantum space, and the multiplication here could be modified also by some algebra morphism, which is defined here using C, and the lambda from the quantum group. And the action is modified, and it involves these Q numbers. Okay, maybe you can go further, and just to say a few words about some categorical point of view. This Hom-type algebra was first studied by Stefan Kanepel and his student Goiber, where now in fact this allows us to get some new categories. This is then if you consider a monoidal category, then you can associate to this monoidal category a new category where the objects now are pairs. Pairs of an object of the category C and an automorphism of this object. And this category is denoted by H tilde C, and it has non-trivial associativity, constraint. And then now if you consider as C the category of linear space over a base field K, then what is the algebra inside this category? The algebra in this monoidal category, which is symmetric as well, is a Hom-associative algebra. But here, of course, since we are dealing with the automorphism, the alpha here should be bijective. That's why this monoidal Hom-algebra uses only automorphisms. And with people from Ferrara, with Claudia Minini and the student Gratiani, and from Imparniti, we extended this construction by considering action of a group. Then we consider a monoidal category and a group, and also we need two elements in the center of this group. And we constructed a new category, which we call Hom group category, because it involves a group and homomorphism. And the objects here are pairs. An object of the category C and FA are group homomorphism going from J to the automorphism of A. Okay. Then, of course, here the associativity constraint is also modified, and it involves all this data, and we can construct a breaking here. And now, if for group G we consider Z, then what we get here is exactly the construction done by Kanepel and Goiber. And now, if we consider another example, if we consider Z times Z, and as element C 1, 0, and 0, 1, 0, 1, and now again we consider linear spaces over K, then we can see that these Fm elements are generated by values on 1, 0, and 0, 1. And we call this alpha, this image alpha m, and this one beta m inverse. And then for the objects, now the objects in this category, z times z m k, that could be identified to triples now, m alpha m beta m, and this alpha m and beta m should commute. And now if we take three objects in this category, you can see that this associativity constraint is modified, by these alphas and betas. And we can also construct a braiding, which is modified by these alphas and betas. And what we will get here is an additive braided monolithic category. And now, what is the concept of algebra inside this category? If we do this, that what we get, and what we get is a new type of algebra now involving two maps, and we call this Bi-Hom-associative algebra for associative algebra. And if you remember, I showed in the beginning what we called Hom-associative algebra. To the left we have alpha A dash, and 2 dash, and on the right we have the same alpha for Hom-associative algebra, but now we allow us to take different different twist maps. We have two twist maps. To the left you have alpha, and to the right you have beta. And of course, in the definition now we assume that all these beta, alpha commute. And they are also algebra maps. Okay? Then this is the definition of Bi-Hom-associative associative algebra. And for unitality, also it's a bit from the left we use both alpha and beta. It depends of one is from the right. If one A is on the right, we say that this is alpha A, and one is on the left. Then we say that this is beta A. This is the unitality for this type of algebra. And of course, for now, what is the corresponding Bi-Hom-Lie algebra? It's also a little bit complicated. Then it's defined now by the bracket, and now two maps again. And these two are these two maps should be, and this should be algebra maps. And now the skew symmetry is different. We don't have the usual skew symmetry, but it's a skew symmetry using beta and alpha. And we have the bracket of beta alpha, beta A alpha A dash. This should be minus beta A dash alpha A. And also the Jacobi condition was modified. Okay? Then one can expect whether when you go from Bi-Hom-associative algebra, you get.
What about one concrete? For example, your free algebra in the previous case, you had decorated trees. So in the Bi-Hom case,
you can decorate by more colors. Then you have pairs.
I see.
Then what you need here is that you have pairs. Then you take two elements. And one corresponds to the power of alpha, and the other to the power of beta. And now with the commutator is also modified in this situation, and we get from Bi-Hom-associative algebra a Bi-Hom-Lie algebra by considering this bracket. And also now, what do we have some corresponding Yao twist? And this is then it works. We can start with Bi-Hom-associative algebra. We can state it here in the general situation. And now what we need is just alpha, beta, which are two multiplicative linear maps, such that they commute, algebra maps that they commute, and then you can twist the multiplication by considering mu composed with alpha beta here, and twist each maps by the first by alpha and the second by beta. Okay, and you get a new Bi-Hom-associative algebra, which we could call the Yao twist of the first one. Okay, and maybe some small tapas like that to say that we can have representation. Models could be generalized, and also several things. I mean, you can.
Is there a Auxil version of some complex? There is some complex Auxil type or something.
Yes, we have. It's not published, but it exists already. We can generalize Hochschild homology and Chevalier-Niebert homology easily in this situation. Yeah. Okay. Now this is the definition of a representation for Homological algebra, but you can generalize it, and here you can have a representation in the endomorphic algebra. Okay, maybe I should stop. Thank you very much.